Good evening, sir.
Good evening, sir.
Good
Good evening, sir.
evening. Good evening. How are we today?
Good, sir.
चल रही है
Okay.
सर जिंदगी.
Okay. Good. Okay. Beta, is the audio video fine?
Yes, sir. Fine.
Okay. All right. I will just give it try to another mic. Just give me a minute. I'll change the mic. Okay, how is the audio now, beta? Any change or same? This one was more clearer. So now better? How is it now?
It's now good, sir.
Okay, beta. All right. Great. Very good. Okay. So beta, today the plan is that first I will start off with the Kepler's laws of planetary motion. And after Kepler's laws of planetary motion, we will go into chart construction, how to construct a Mercator chart. We get questions on both these topics in our paper in question number 8 and 9. So we will see how these questions are to be attempted. And after this, I will show you a presentation on concept of time. We will see what is true sun, what is mean sun, what is equation of time, and what are different types of times which are there. Total 6 times are there: GMT, LMT, GAT, LAT, GST, LST. So I'll give you a brief intro on what these times are, so that if by any chance any question comes which is based on these times, so you will be able to handle it well. So that's the plan. And before I go into Kepler's laws, I will show you a typical question on stellar magnitude. There's one question which sometime comes in our exams. It is based on the stellar magnitude, and it's little tricky because you need to use a logarithmic formula for solving it. Okay, so that's the plan for today. So ready, beta? Shall we go ahead? We'll do it later, beta. First, let us cover up. Then we will see the doubts. Okay, all right. So let me put up the presentation. Now, the first concept which we are going to look into is the concept of stellar magnitude. Now, we are aware stellar magnitude is basically a scale which gives us the apparent or relative brightness of different celestial bodies. Let's see the question. The question says star A has a magnitude of minus 0.8 and it is 30 times brighter than star B. Find the magnitude of star B. Now, all these questions which we are discussing are picked up from the past papers. So let us see how do we attempt this question. Now, for doing this question, we need to be aware of two things. Number one, that the stellar magnitude gives us a formula or a relationship with which we can find out how many times a particular body is brighter or dimmer than the other body. What is that formula? The number of times a star is brighter than the other is given by the formula 2.51 raised to power the difference of their magnitudes. So this is the formula which we will be using in this question. Now, second concept which we need to be aware of, which we have done in our school time, that is a logarithmic concept. That formula, logarithmic formula, is log of a raised to power b is equal to b multiplied by log of a. So this is a logarithmic formula which we will be using, which we need to use to solve this particular question. So once we are aware of these two things, the question can now be solved. First of all, let's assume that the difference of magnitudes between the two bodies is x. If the difference of magnitude between the two stars, star A and star B, is x, that tells us 2.51 raised to power x should be equal to how many times one star is brighter than the other. Now this is given to us in the question. The question says that star A is 30 times brighter than star B. So this tells us 2.51 raised to power x is equal to 30. Now we want to solve this relationship for x. So for this, what we do is we take a log on both the sides. So this gives us log of 2.51 raised to power x is equal to log of 30. Now applying the logarithmic formula which we saw, log of a raised to power b is equal to b multiplied by log a. Similarly, you see log of 2.51 raised to power x is equal to x multiplied by log of 2.51, and this is equal to log of 30. Now keeping x on one side and taking the other items on the opposite side, we get x is equal to log 30 upon log of 2.51. We can easily solve this using our scientific calculators. So when we solve this for x, it gives us the value as 3.6958. So this x, which was assumed to be the difference of magnitude between star A and B, has been found to be 3.6958. Now it is given that the magnitude of star A is minus 0.8. The difference is 3.6958, and since star B is dimmer, it is given in the question, star A is 30 times brighter than star B. So this tells us that the star B is a dimmer star. Now, since it is dimmer or less bright, its magnitude number will be greater than the magnitude number of A. We know that the stellar magnitude scale is a reverse logarithmic scale. That means as the brightness increases, the magnitude decreases. And as the brightness goes down, the magnitude number increases. So this tells us that star B, which is dimmer, its magnitude number should be greater than the magnitude of A. So magnitude of A was minus 0.8. The difference between the two is 3.6958. This is the difference between magnitudes of A and B, and magnitude of B has to be greater than the magnitude of A. So what we do is we add this difference 3.6958 to the magnitude of A, which is minus 0.8, giving us a value of 2.8958. So this is the magnitude of star B. So you can see now star B magnitude 2.8958, star A magnitude is minus 0.8. The difference between both of them is 3.6958, and if you use that difference in this equation, 2.51 raised to power this difference, it will give you the value of 30. So this is how the question is solved. Any doubts in this, beta? Great, beta. Very good.
सर ये log 30 by log 2.51 कर रहा हूँ तो सिंटेक्स एरर आ रहा है
बेटा ब्रैकेट लगा रहे हो?
यस सर
Should not come, beta. Log 30 divided by log of 2.51.
समथिंग रॉन्ग सर कैलकुलेटर में सेटिंग्स में कुछ गड़बड़ लगता है
What about others, beta? Just try it out.
Sir, coming, sir. 3.695.
Coming, sir.
Okay, all right, beta. Check the settings,
sir,
beta.
3.
Good. Okay, good. Good you noticed it now. At least it will not bother you in the exams. Okay, all right. Let's move ahead. Now moving further, the next set of questions is based on Kepler's laws of planetary motion. So there are three laws which basically give us an idea about the motion of planets around the sun in the solar system. So before we go into the numerical, let us discuss about Kepler's three laws of planetary motion. Okay, before we move ahead, beta, is the audio coming okay? I am on a different system today, so audio is fine, beta?
Fine, sir, fine.
Okay, all right. The first law of Kepler states that all the planets revolve around the sun in elliptical orbits. So as you can see, we have this blue color planet revolving around the sun in an elliptical orbit. The green color orbit which we see in the diagram is having elliptical shape. Now before Kepler, people used to believe that the orbits of planets are circular, but Kepler's with his observations proved that these orbits are not circular but elliptical. Though the ellipticity of these orbits is very, very less, they are very close to a circular shape, but still they are not exactly a circle. They are not exactly circular. They are actually elliptical. Now, just as a circle has one center, the ellipse, on the other hand, has two reference points, and these reference points are known as focus. So it has focus 1 and focus 2. In plural, it is known as foci. So all the planets revolve around the sun in elliptical orbits. Every elliptical orbit has two foci, and sun is situated at one of the foci of the ellipse. The other foci is blank. There is nothing there. But sun is situated at one of the foci of the elliptical orbit of all the planets. This is Kepler's first law. Now moving on to Kepler's second law. Kepler's second law states that the radius vector of a planet sweeps out equal areas in equal intervals of time. Let us understand with the help of a diagram. We see the sun as the yellow circle in the middle of the diagram, and then we see a elliptical orbit of a particular planet, and in this elliptical orbit, Let us assume that on a particular day when we started our observation, the planet was at this particular location. You can follow the laser pointer. So let us assume that on one particular day when we started observing the planet was at this particular location where the laser pointer is right now. Now, if the planet is at this location, the radius vector of the planet is this one. You can follow the laser pointer. This is the radius vector of the planet. Now, after that, the planet starts to move. We keep on observing the planet day after day. And let us say after 30 days, we again make our observation and the planet has reached up to here. Now, in this interval of 30 days, the radius vector of the planet has covered an area which is shaded in blue. This is the area swept by the radius vector of the planet in a duration of 30 days. Now, after this, the planet, we stop our observation. The planet keeps on moving on its orbit. Now, when you are moving on an elliptical orbit, at some places you will be far away from the foci, which is basically the sun, and at some places you will go closer to the foci. In a circle, all the points on the circumference are equidistant from the center, but in an ellipse, the track of the ellipse sometimes goes closer to the foci, to a particular foci, and sometimes goes away from the foci. So the planet moves further and it reaches at this particular location where the laser pointer is right now on a certain day, and we start our observation again. Now we start our observation. This is the radius vector of the planet right now. The planet continues to move and we keep observing the planet for the same duration of 30 days. Now, after 30 days, we observe that the planet has reached up to this particular point. And you can see this is the radius vector of the planet now. The area which is swept by the radius vector of the planet in the same duration of 30 days is represented by this blue color sector. So you can see the two different sectors as the areas swept out by the radius vector of a planet during its two different locations in its orbit. Now Kepler said that the area swept out by the radius vector of the planet in equal intervals of time will be equal. So the area of this blue sector will be equal to the area of this blue color sector. Both their areas are going to be same. Now, what does this tell us about the motion of the planets in its orbit? Now, if the planet has to sweep out equal areas in equal intervals of time, the planet will have to move faster in its orbit when it is closer to the sun. You see, at this particular location, the planet is much closer to the sun as compared to the previous observation. So with the planet being much closer to the sun, you see the length of the radius vector is much smaller as compared to the previous case. Now with the length of radius vector being much smaller, if it has to sweep out equal area, it has to move at a much faster pace or much faster speed in its orbit. Now, when the planet is far away from the sun in this particular condition, you can see the radius vector is very, very long as compared to the radius vector in the previous instance. Now, with the radius vector very, very long, if it has to sweep out equal area in equal interval of time, the radius vector of the planet has to move very slowly in this part of its orbit. So, it gives us an indication that the planet moves faster when it is closer to the sun. You can see this is the sector where it is closer to the sun, and the planet has moved quite fast in its orbit. And when the planet is far away from the sun, it will move very slowly as compared to the previous instance. So the motion of the planet, or the speed with which it covers its orbit, is not constant or fixed. The planet keeps on changing its speed. It becomes slow when it is far away from the sun, and it gains speed, it picks up speed and becomes faster when it is closer to the sun. So this is Kepler's second law of planetary motion. The radius vector of a planet sweeps out equal areas in equal intervals of time, indicating to us that the planet will be moving faster in its orbit when it is closer to the sun, and it will be moving slower in its orbit when it is farther away from the sun. Any doubts, beta? Very good. Now moving on to Kepler's third law of planetary motion. Kepler's third law basically gives us the relationship between the mean distance of a planet from the sun, which is also known as its orbital radius, represented by alphabet R, and the time it takes to complete one revolution around the sun, which is also known as its orbital period, represented by alphabet T. So the third law gives us a relationship between the orbital radius and the orbital period of a particular planet. What does the law say? The law says that the square of a planet's orbital period is proportional to the cube of the mean distance of the planet from the sun. In other words, T square is proportional to R cube. It can be denoted in this particular relationship. T square upon R cube is constant, can be considered as K. T is the orbital period of a planet. Let's say, for example, if you take the case of the Earth. So in the case of Earth, the orbital period is 365.25 days. And R is the orbital radius, mean orbital radius of a planet. In case of Earth, the mean orbital radius of the Earth's orbit around the sun is 93 million miles, or 93 into 10 raised to power 6 miles. So this is the relationship given by Kepler's third law of planetary motion. T square by R cube is equal to constant. This is a very important relationship, and we get numerical question based on this particular relationship. Now, how can we utilize this relationship in the numerical questions? Now, for using this relationship, we need to be aware of the orbital time, or the time Earth takes to complete one orbit around the sun, and the orbital radius of the Earth. Now, we know that the time period, orbital time period of the Earth is 365.25 days. And we know the orbital radius of the Earth is 93 billion miles, which is 93
Sir, your voice is coming.
power 6 miles.
Sir, your voice is breaking, sir.
What about other people, Peter?
ब्रेक हो रही है शुरू वॉइस।
अभी ठीक आ रही है सर। जब आप ये थर्ड लॉ का ये बता रहे थे इक्वेशन तो ब्रेक हो रहा था।
ओके, गिव मी अ मिनट। So t square upon r cube of Earth converts to 365.25 square divided by 93 into 10 raised to power 6 cube. How was it now, beta?
Sir, now okay, sir.
Okay, all right. This, being constant for each and every planet, should be equal to t square by r cube of any of the planets of the solar system. If you look carefully now in this relationship, t square by r cube of Earth is known to us. If we are given the orbital radius or the orbital time period of any of the planets, one of these two items is provided to us. By using this relationship, we can easily find out the second unknown item. If the orbital time period of a planet is given, we can put that in this relationship and we can obtain its orbital radius. And the opposite is also true. If they provide us with the orbital radius of a particular planet, we should be able to calculate the orbital time period of that particular planet. Now for this, you need to be aware of these two values, the orbital time period of the Earth, 365.25 days, and the mean orbital radius of the Earth, 93 into 10 raised to power 6 miles. These figures are not given in the question. It is expected that the candidate is aware of these figures to be used in a numerical based on the Kepler's laws. Clear, beta? Any doubts? Very good.
So this radius or orbital period, with this equation, we will get the distance or orbital period from the Earth between the planet, not from the Sun, correct, sir?
No, beta, it will be from the Sun, beta. All the planets are revolving around the Sun, so the orbital radius is from the Sun, beta.
Yes, sir, but this equation we are doing with the Earth, correct?
No, see, what you are doing is you are comparing t square by r cube of Earth with the t square by r cube of any other planet. This 93 million miles is the distance or mean orbital radius of the Earth's orbit. So this r which you will be calculating will be the mean orbital radius of that particular planet, which will be from the Sun.
Okay, so it's like a relative.
Right, that's right.
Okay, sir.
Okay. Now, next we refer to some planet configurations. Configurations basically means a particular location of the planet in its orbit. So the terms which are used to represent or show planet configurations are conjunction, number 2 opposition, and number 3 quadrature. They basically tell us about the position of a planet with respect to the Sun. Let us now understand all these three configurations or all these three terms with the help of a diagram. Let's show the sun in our diagram. Then around the sun we show planet Earth. I have shown it in blue color. Our Earth is a blue planet. And let's show the orbit of the Earth now. We have the orbit of the Earth on the diagram. Now let's show another planet of the solar system. We show the red planet, and it is the Mars planet. We are aware that the orbit of Mars is greater than the orbit of the Earth. So let's now show the orbit of the Mars. We have the orbit of the Mars in our diagram. Now both Earth and Mars are revolving around the sun in their orbits. The speed at which they are revolving around the sun is different. They are revolving around the sun with different speeds. All the planets have different speeds. We just saw the third law of Kepler's planetary motion, which said t square by r cube is equal to constant. So as the radius keeps on increasing, the time period also keeps on increasing. So that tells us that the angular speed with which the planets revolve around the sun will also keep on changing from planet to planet. Now with varying speed, it is possible that the Earth and a particular planet may be at different locations with respect to the sun. Like for example, right now when you see in the diagram, you can see that for an observer on the Earth, the sun as well as the planet Mars are in the same direction. Both the sun and planet Mars are in the same direction. Now this particular placement of the planet with respect to the sun is called as conjunction. We say that this particular planet or planet Mars is in conjunction with the sun. So this is the meaning of the first term, which is conjunction. Basically means that the planet is in the same direction as the sun. The planet is in conjunction with the sun. Now let's say after some time we keep on observing this particular planet, and this particular planet moves to a different placement in its orbit, and right now the planet has moved to this particular placement, this particular location in its orbit. Now for an observer on the Earth with the planet Mars at this particular location, you can see now that the sun and the planet Mars are opposite to each other, or they are in opposite directions. The sun is in one particular direction and the planet Mars is exactly in the opposite direction. Now this particular orientation is called as opposition. We say the planet Mars is in opposition to the sun. So opposition basically means that that particular planet and the sun are in totally opposite directions. Now let's assume that the planet keeps on moving in its orbit with some relative speed, and at another particular instant we observe that the planet Mars is at this particular placement or location in its orbit. Now if you observe this planet Mars carefully, you see the direction in which the planet Mars is at right angles to the direction in which the sun is. So whenever a planet is at right angles to the direction in which the sun is, it is called as quadrature. So this is the planet Mars in quadrature. The direction in which the planet Mars is 90 degrees away from the direction in which the sun is. Now there is a possibility, another possibility of quadrature. If the planet Mars at a particular instant reaches to this location in the diagram. You can follow the laser pointer. So at this particular location also, the direction in which the planet is at right angles to the direction of the sun. So it tells us that this particular planet is in quadrature with the sun. So conjunction means the sun and a particular planet are in the same direction or the angle between them is 0. Opposition means that the direction in which the sun and a particular planet are exactly opposite to each other, or the angle between the sun and that particular planet is 180. And quadrature means that the direction in which the sun is 90 degrees away from the direction in which the planet is, or the angle between the sun and the planet is 90 degrees. Now these terms are important from the point of view that whenever we get numerical based on Kepler's laws of planetary motion, sometimes these concepts are used in the question. So we should be aware of what these terms means to accurately solve that particular question. So this is the importance of understanding these terms. Now the next important concept which we have is the concept of elongation. Let's understand what elongation is. Elongation of a planet is the angle at the center of the earth between the sun and that particular planet. Let's try to understand it with the help of a diagram. We have the sun in our screen now. Let's show the planet Earth. We can also mark off the orbit of planet Earth. You can see the orbit of Earth in blue color. Now let's show another planet. In this case, we show planet Venus. Now Venus is closer to the sun as compared to the Earth. So let's now mark off the radius of the orbit of Venus also. You can see the orbit of Venus in maroon color as shown by the laser pointer. Let's now try to show the radius vector of Venus as well as Earth. So you can see this dotted line joining the center of Sun with the center of the Venus. This marks off the radius vector of planet Venus. Similarly, you can see this blue color dotted line showing the radius of the Earth. Now let's draw another line joining the center of the Earth and the center of the planet Venus. So you can see this red color line joining the center of Earth with the center of Venus. Now from this diagram we can easily understand what elongation is. You see this red highlighted angle in the diagram is what is elongation. Let's try to match with the definition of elongation. The definition says elongation of a planet is the angle at the center of the Earth. You see this red angle is being made at the center of the Earth between the sun and the planet. So from the center of the Earth, a line joining the center of the sun and a line joining the center of the Venus, angle between those two lines is the elongation. So angle at the center of the Earth contained between the sun and that particular planet is known as the elongation of that particular planet. Now as Earth and Venus are moving with different orbital speeds, different angular velocities in their orbits, their location with respect to each other will keep on changing. The planet Venus could be at any particular elongation depending upon what is its position in its orbit. Let's assume that if planet Venus is at this particular position here, the elongation will be the blue color line showing the radius of the Earth, and the line joining the center of the Earth with the location of Venus at this particular point. If Venus is at this particular location here, the elongation will again be by the angle between the radius of the Earth and the line joining the center of Earth with center of the Venus. Now, if you look carefully, that as the planet Venus moves in its orbit, you can follow the laser pointer. At this particular point, Venus will be in conjunction with the Sun, or the elongation will be 0 degrees. Now, as it moves in its orbit, the elongation will start to increase. At this particular point, at the first location, it will have a certain elongation. After this, the elongation will keep on increasing. Now, if you look carefully, at this particular point, Venus will have the maximum elongation. The angle at the center of Earth will be maximum at this particular placement of Venus in its orbit. As Venus moves forward in its orbit, you see the elongation will start to reduce again. Now, this point where the maximum elongation occurs, if you look carefully, you will see it is the point where from the center of Earth, if you draw a tangent to the orbit of Venus, the tangent meets the orbit of Venus at this particular point. This is the point where Venus is going to have maximum elongation. And we are aware that the tangent is always perpendicular to the radius of a circle. So this line joining the center of Earth with the center of the Venus, the red dotted line, represents a tangent, and this line joining the center of Sun with the center of Venus represents the radius of the Venus. So they will be at right angles. So this angle here at planet Venus will be 90 degrees. So this is the point of maximum elongation of Venus, and we know at the point of maximum elongation, the angle made at point Venus between the Sun and the Earth would be 90 degrees. Now, this particular diagram is used in solving some of the questions. So you should be clear about the concept of maximum elongation and what is this angle which is made at the planet at the time of maximum elongation. Now, if you consider a exterior planet means the planet whose radius is greater than the radius of the Earth, like say for example Mars. Now, the maximum elongation of Mars is going to be 180 degrees. The maximum value of elongation is possible, which it can be, is 180 degrees. For a exterior planet like Mars, it can reach up to its maximum elongation, that is 180 degrees when it is in opposition to the Sun. But for a inferior planet like Mercury or Venus, the maximum elongation will be less than 90 degrees, and it will depend upon the radius of that particular planet and the radius of the Earth. Now, inferior planets like Venus, as you see in this diagram, can never be in opposition to the Sun. They can never be in opposition. Irrespective of whichever position they are in their orbit, they can never go in a direction which is opposite to the direction of the Sun. And at the same time, if you look carefully, you will observe that these inferior planets like Mercury and Venus can also never be in quadrature with the Sun. To be in quadrature, the angle at the center of the Earth or the elongation has to be 90 degrees, which is not possible in this particular case. So opposition and quadrature can only be attained by exterior planets whose radius is greater than the radius of the Earth. And for inferior planets like Mercury and Venus, whose radius is less than the radius of the Earth, they can never be in quadrature and in opposition. Any doubts up to here, beta?
Sir, the angle is 180 degree. Elongation is 180 degree for the exterior planet.
The maximum elongation in case of a exterior planet can be 180 degrees, beta.
सर वो डायग्राम से बता सकते हो सर? I'm not able
Okay,
to
beta.
imagine.
Okay. अभी दिखा देता हूँ बेटा. So you have understood elongation, na? Angle at the center of the Earth.
Yes, sir.
Okay, all right. Let me show you a exterior planet. ये देखो बेटा, अब इस डायग्राम में हमें मार्स दिखाई दे रहा है. The radius of the Mars is greater than the radius of the Earth. Now you see when Mars is in opposition, beta. Look at the opposition. Tell me what will be the elongation of Mars at opposition?
180.
180 degrees. That was what I was saying, right?
Yes, sir.
Clear now, beta?
Right. Yes, sir.
Okay, great. So with these now, beta, you should be able to solve the Kepler's laws based numerical questions. So these were the fundamentals of Kepler's laws which are used for solving the numericals.
Sir, can you show the previous slide, sir?
Okay, beta. Before this,
Last one, sir, about Venus, sir.
Okay, this one.
Yes, sir. There is two more position for Venus, sir. One is
Right,
less
beta.
than 90 and other is more than 90, sir. That is also the elongation position.
In those positions,
This one or the other one, sir, also, sir.
Okay. Beta, ये जो दोनों positions हैं, elongation will be happening here also, but it will not be the maximum elongation. Okay. Maximum elongation will happen only at this location where
Up to 90.
you have the tangent point. In the remaining two locations, the elongation will be lesser than the maximum elongation.
Okay, sir.
Okay, beta? Clear?
Yes, sir.
Okay, great. Very good, beta. So these were the concepts of Kepler's laws. Now let me take you to the fundamentals of chart construction. We now move on to our next topic, which is based on chart projections. Now the questions which we get on this topic are related to construction of a Mercator chart. We are given a particular area. The coordinates of that area are given to us, latitudes and longitude, and we are required to construct a Mercator chart on a particular given scale for that particular area. Now for solving this question, we need to be familiar with the concept of Mercator chart, how the scales are used on a Mercator chart. So let's have a look. Let's see a Mercator chart here on the screen. You can see a small part of the Mercator chart here on the screen. Now a Mercator chart is based or constructed basis two scales. You see one of the scales, the horizontal one, which is at the bottom of the chart, is known as the longitude scale. And you see a vertical scale also on the right side of the chart. The vertical scale is the latitude scale. Now both these scales, the latitude scale and the longitude scales, are different from each other. these scales are not same, they are different from each other. By different, we mean that 1 minute of longitude will not be equal to 1 minute of latitude. They will be different from each other. The length of 1 minute of longitude or 1 degree of longitude will be different from the length of 1 minute of latitude or 1 degree of latitude. Now, out of these two scales, the latitude and the longitude scale, the longitude scale remains constant throughout the chart. So it basically means that the length of 1 minute of longitude remains the same throughout the chart. You can go to any part of the chart, the length of 1 minute of longitude or 1 degree of longitude will remain fixed. It is not going to change. As far as the latitude scale is concerned, the latitude scale is not fixed or not constant. The latitude scale keeps on changing depending upon where you measure it on the chart. If you are at the equator, the latitude scale is exactly equal to the longitude scale, or you can say when you are at the equator, the length of 1 minute of latitude is exactly equal to the length of 1 minute of longitude on the chart. But as you go in higher latitudes, as you go towards the pole, the length of 1 minute of latitude keeps on increasing. Now, both these scales have a relationship between them, and this relationship is given by the formula. The latitude scale is equal to the longitude scale divided by cos of latitude. Now, this can be further simplified as the length of 1 minute of latitude on a Mercator chart is equal to the length of 1 minute of longitude on a Mercator chart divided by cos of latitude. So using this relationship, you can find out the length of 1 minute of latitude or the length of 1 minute of longitude if any one of them is known to you. So this is a very important relationship, and we will be using this relationship for the construction of our Mercator chart.
Excuse me, sir.
Go ahead, beta.
Sir, here you told longitude scale will be constant, sir. And other thing you said latitude scale increasing towards poleward. But
Right, beta.
if we see in Earth has a spherical figure, so
Right.
if we are going towards the pole, it will be decreasing, no, sir? Or am I wrong, sir? Here, for
No, beta, no,
longitude
you are right.
is
You are
also
right.
on the meridian. So when we are going to equator, it will be maximum, and then we going to towards pole, then it should be reduced, something like that, sir.
Now you see, beta, what happens on the surface of Earth is different from what happens on the chart. On the surface of Earth, the latitudes are fixed. 1 minute of latitude is equal to 1 nautical mile. It remains the same when you go towards the pole. What changes on the Earth's surface is the longitude. The longitude distance between two longitudes or east-west distance between two meridians starts to reduce as you go towards the pole. But it does not happen that way on a Mercator chart. Mercator chart has some anomalies. It is not a exact replica of the Earth's surface, beta. So there are some distortions in the Mercator chart. Because of that, the longitude scale on a Mercator chart is fixed. The latitude scale is what changes on the chart.
Okay, sir. So longitude will be fixed, only latitude scale will be changing.
That's right, beta. That's right.
Okay, sir. And latitude we will calculate by here, the formula, whatever you are giving, longitude scale divided by cos latitude. Okay.
That's right. This is a relationship basically, which gives us the relationship between longitude scale and lat scale.
So sir, this one is just for the Mercator chart, but when we are taking distance on the in the chart work, that time we use only the latitude, right, sir?
That's right, beta. Distance is always measured on the latitude scale. And in chart work also, you remember when we pick up the distance, we always keep it close to the meridian, close to the latitude where both the positions are. We never go too much up and down from there.
Okay, sir. Okay.
Okay, great. Go ahead, beta. We have to find that, beta. What we will be given is the scale of the chart, and the scale of the chart is related to the latitude length or length of 1 minute of latitude. We will be finding the length of 1 minute of longitude and using this as a building block of our chart. Okay, I will show you how it is used. We will be using this exact same formula. So remember this formula. Okay. Now, before we go into the numerical, let's first understand some of the basic definitions. They really helps us in understanding the concepts as well as in the numerical also. The first definition which we have is the definition of meridional parts, in short also known as MP, Mike Papa. So what are these meridional parts? It is the length of the meridian between the equator and that particular latitude. Meridional parts are reference to latitude. Every latitude will have a meridional parts value. So it is the length of the meridian between the equator and that latitude measured in units of longitude scale. Or you can also explain it in a different wording, in a different way. That is, the number of times 1 minute of longitude can be laid between the equator and that particular latitude. So the number of times you can place 1 minute of longitude from the equator up to a particular latitude is what we call as meridional parts for that particular latitude. How do we obtain them? We have a meridional parts table in the Norris Nautical tables. So they can be picked up from there. You enter the table with latitude, and for every particular latitude, degrees and minutes, they will give you the meridional parts for that particular parallel. Now moving on to the second definition, that is DMP. It is difference of meridional parts. The DMP or difference of meridional parts between two parallels is the length of the meridian between the two parallels measured in units of longitude scale, or you can have a different wording again as we had in meridional parts. This was the first definition explained in one way. You can also explain it the number of times 1 minute of longitude can be laid between those latitudes. This is known as the DMP, difference of meridional parts. The third definition which comes ahead is the natural scale of the chart. Natural scale of the chart is the ratio of distance between 2 points on the chart and the actual distance between them on the earth surface. So that is the natural scale of the chart.
The difference between DMP and MP.
Beta, meridional parts or MP will be for one particular latitude. Like you can have MP for 10 degrees north or MP for 20 degrees north. DMP is the difference. DMP will be between two particular latitude. Like what is the DMP between 10 and 20 degrees north? So that is the difference between the two.
Okay, sir. Thank you.
Okay. Now with the basics of chart projections clear in our mind, we are now ready to go into solving of a question. We have the question on the screen now. The question says, construct a Mercator chart from 28 degrees north to 32 degrees north and 015 degrees west to 020 degrees west using a scale of 1:3 million or 3,000,000 in latitude 30 degrees north. So we are required to construct a Mercator chart. The coordinates of the area are given to us, latitudes from 28 to 32 degrees north. The meridians are 015 to 020 degrees west. The scale is also given. The scale is 1:2 or 1/3 million, 3,000,000. The scale basically means that 3 million units on the Earth's surface is equal to 1 unit on the chart. Or you can understand it in this way, 3 million centimeters on the Earth's surface will be equal to 1 centimeter on the chart. Now, whenever a scale is given, it will always be referenced to a particular latitude, and in this case, the scale is referenced to 30 degree north latitude. Now, let's see how do we solve these questions. The first and foremost step which we follow in these questions is to calculate the length of 1 minute of longitude or 1 meridional part on the chart. What is the length of 1 minute of longitude on the chart? Or what is the length of 1 meridional part on the chart in millimeters or in centimeters? Now, why we are calculating 1 minute of longitude? We are calculating 1 minute of longitude because it forms the basic building block of our chart. We have just now seen that the longitude scale, or you can say the length of 1 minute of longitude, remains constant throughout the chart. Whichever part you go, the length of 1 minute of longitude is going to remain the same. So we take this 1 minute of longitude or 1 meridional part as our building block, and using this we construct the entire chart. We cannot use the latitude scale here because if we use 1 minute of latitude, we are aware that in different parts of the chart, the length of 1 minute of latitude keeps on changing, thus making it difficult for us to construct the chart. Now, how do we find out this length? We are aware of the definition of 1 nautical mile. 1 nautical mile on the Earth's surface is basically equal to 1 minute of latitude, and it is of a fixed distance, and that distance is 1852.3 meters. So exactly that same thing is mentioned here. The length of 1 minute of latitude on Earth is equal to 1 nautical mile. That is the definition of a nautical mile, and it is equal to 1852.3 meters. Now let's convert into millimeters. That will be much easier for our reference. So 1852.3 meters converts to 1852300 millimeters. Now we have seen the length of 1 minute of latitude on Earth. Now what is going to be the length of 1 minute of latitude on the chart? Now for this, we have to multiply this distance by the scale of the chart. So 1852300 multiplied by the scale. The scale is 1 upon 3 million. So the same thing is mentioned here, 1852300 multiplied by 1 upon 3 million, and it gives us a value of 0.61743333 millimeters. We have taken it up to a high accuracy because that makes our calculations all the more accurate. Now, once we find out the length of 1 minute of latitude on the chart, now we can use the formula. We are aware of the formula that length of 1 minute of latitude is equal to length of 1 minute of longitude divided by cos lat. So what is the latitude which is used in the formula? It is the reference latitude on which the scale is based. In our question, the scale is based on a reference latitude of 30 degrees north. So that is what we will be using here in the formula. So putting the values here, 1 minute of latitude was 0.61743333 is equal to length of 1 minute of longitude, which we will be calculating now, divided by cos of latitude, which is cos of 30. So using these two values, we get the length of 1 minute of longitude on the chart, and it comes to be 0.534712951 millimeters. Now this is also equal to the length of one meridional part, in short known as MP, Mike Papa. One meridional part is nothing but exactly same as 1 minute of longitude. So once we have this length now of 1 minute of longitude, we can easily construct the chart. Any doubts up to here, beta? Very good. So proceeding ahead on construction of our chart now. We have just now calculated 1 minute of longitude or one meridional part on our chart measures 0.534712951 millimeters. Now, since we have the length of 1 minute of longitude, we can easily find out the 1 degree of longitude. 1 degree of longitude is 60 minutes. So this multiplied by 60 gives us 32.1 millimeters. So we obtain the length of 1 degree of longitude equal to 32.1 millimeters. Now you can round off this value to one place after the decimal for millimeters. Now once we have this value known to us, 1 degree of longitude, we can now draw the meridians for our particular area. So let's now draw the meridians. We have to cover an area from 15 degree west to 20 degrees west. So I'm going to first draw the meridian of 20 degrees west. I have drawn it to the left side of my diagram because this is the westernmost longitude. So you can see 20 degrees west meridian coming up. Now to draw the next meridian 19 degree west, I need to know what distance in millimeters should I keep between the two, and that has been calculated to 32.1 millimeters. So keeping a gap of 32.1 millimeters, I draw another vertical line parallel to the first meridian, and that gives me my next meridian of 19 degree west. Now moving further in the same fashion, keeping the same distance, I draw a meridian of 18 degrees west. The distance remains the same, 32.1 millimeters. Because the longitude scale is constant, 1 minute of longitude or 1 degree of longitude remains the same throughout the chart. Exactly in the same way, keeping 32.1 millimeter distance, I draw the meridian of 17 degree west. Then keeping the same distance, 16 degree west, and keeping the same distance, I draw a meridian of 15 degree west. So we have all the meridians of the required area in our plot, in our diagram. Now we can also show the latitudes. We have to show the latitudes from 28 degrees north to 32 degrees north. So let us first of all draw the lowest latitude, 28 degrees north. I'm going to draw this 28 degrees north at the bottom of the plot. So you can see this green color line coming up. It represents 28 degrees north parallel of latitude. Now the question which I face is, how much gap should I be keeping between 28 north and 29 north? Now I do not know what is the length of 1 minute of latitude. So how do we find out the length or distance to be kept between 28 and 29? Now for this, what we do is, we find out the difference of meridional part between these two latitudes, 28 degrees north and 29 degrees north. This can be found from the meridional parts table in the Norris table. So if we find the meridional parts for 29 degrees, it comes to 1808.09, and we see the meridional parts for 28 degrees, it comes to 1740.18. The difference between them comes out to 67.91. So the difference of meridional part between 28 and 29 is 67.91 meridional parts. So there are 67.91 meridional parts to be placed between 28 and 29, or you can also say 67.91 minutes of longitude which are to be placed between 28 and 29. Now we know the length of 1 minute of longitude is 0.534712951. So for 67.91 minutes of longitude, the length is going to be 67.91 multiplied by 1 minute of longitude in millimeters, and that gives us a distance of 36.3 millimeters. So if I keep a distance of 36.3 millimeters from my bottommost latitude parallel 28 degrees north, I can now draw the next parallel of 29 degrees north. Now following the same procedure between 29 and 30. Now be careful here. The gap between all the meridians remained the same throughout the chart, but the gap between the parallels of latitude will not remain same. So we will have to calculate the gap between two parallels for every latitude. So let's try to find it out for 29 and 30. Now we get the DMP. The DMP is 1876.67 for 30 degrees north, 1808.09 for 29 degrees. The difference comes out to 68.58. Multiplied with the length of 1 minute of longitude gives us a gap or distance of 36.7 millimeters. So you see it has increased from 36.3. Though the increase is very, very marginal as far as our resolution is concerned, but still this calculation needs to be shown in the question. The examiner is specifically looking for this distance which you are calculating. So keeping this distance of 36.7 millimeters now, you mark off a parallel of 30 degrees north. Now to do exactly the same thing for 30 and 31, we find out the DMP from the Meridional Parts table. The DMP comes to 69.1.
The voice is buffering. Buffering.
Same issue again.
You can see now it has increased from 68.58, and multiplying this value 69.29 with 1 minute of longitude gives us a distance of 37.1 millimeters. So this is the distance to be kept between 30 and 31. So let's keep a distance of 37.1 millimeters and mark off the next parallel 31 degrees north. Moving further between 31 and 32, exactly in the same fashion, DMP comes out to be 70.02. You can see it is greater than 69.29, and multiplied by 1 minute of longitude gives us a distance of 37.4 millimeters. And at this particular distance, we can now draw the parallel of 32 degrees north. So for this beta, keep it clear in your mind the definition of DMP. DMP is the difference of meridional parts, or number of times 1 minute of longitude can be placed between the two latitude. So once you have the DMP and you have the length of 1 minute of longitude, the distance between any two parallels can be easily calculated. And you can now see the gap between the parallels is gradually increasing as the latitude increases. So we have the full graticule showing the meridians as well as the latitude, and that completes our construction of the Mercator chart. Any doubts now, beta?
Sir, in the previous slide, we calculated this length of latitude on chart is 0.617. What is the difference between this and that, sir? Now we are calculating the meridional parts to calculate.
Okay. So basically your question is that when we have the length of 1 minute of latitude, why can't we use that here to measure the gap between parallels of latitude, right?
Yes, sir. But also
Okay,
we
beta.
discussed as we go
Okay.
north, it
Hold on. The length of 1 minute of latitude which was calculated was...
30, 31, 31, 32.
Beta, mute your mic,
20,
please.
29.
Okay. Now the difference which we calculate, 1 minute of latitude which we calculated earlier was only applicable for 30 degrees. It is not applicable for 31, for 29. It is applicable only for 30 degrees north. So you cannot use it from 28 to 32 everywhere. It is applicable only for one particular parallel.
okay, sir. Understood.
Okay?
Yes, sir.
Great. Very good. Clear, beta? Any more doubts?
Excuse me, sir.
Go ahead.
Sir, in case if in question they are giving like north to south latitude or east to west longitude, this procedure will be same or it will be make some difference, sir?
Exactly same, beta. Procedure will be same. Let them give you any area. The procedure is going to be same.
Like 0, 1 degree north to 0, 3 degrees south, something like that. Then we'll choose the intermediate like equator. So measuring from equator, some make any differences or it's the same, sir?
It will remain the same, beta. Only thing is when you get the DMP, let us say you are calculating the DMP between 2 degree north to 2 degree south. Okay?
Yes, sir.
So DMP will be meridional parts of 2 added to meridional parts of 2 because the total gap is from 2 north to 2 south. That will be the only difference.
Okay, sir. Because
Right.
then one question came like that, sir. And also if in case this chart scale is not given, then how can we proceed, sir?
Usually the scale should be given in the questions, but if it is not given, then you can pick up a scale of your choice. Make a note in the question that since the scale is not mentioned in the question, we are picking up this particular scale and making the chart. You can pick up a scale of your choice. Okay? Like in this question, the scale was 1:3 million. You can pick up 1:3 million or even 1:4 million, 1:5 million. Any scale of your choice can be picked and the chart can be made.
Okay, sir. Understood, sir.
So the question is construct a Mercator chart covering the area between 2 degrees north and 2 degrees south and between 3 degrees east and 2 degrees west to an appropriate scale at the equator.
Right, beta?
So
Take a scale of 1:5 million. Make a note in the top. Scale is not mentioned, so we are taking the scale and making the chart.
Okay, sir. So in this case, the reference latitude will be 0 degrees.
Yes, that's right.
At the equator.
That's right, beta.
Okay, sir.
Sir,
since there are two hemispheres involved, so our DMP will be added instead of subtraction.
Yes, that's right, beta. Exactly as DLAT is calculated. DLAT between 2 north and 2 south will be 4 degrees.
Yes, sir.
So exactly the meridional parts will also be added.
Copy, sir.
Okay, sir. And scale we can choose anyone, huh?
Yes, beta. Any scale of your choice. If it is not mentioned, make a remark on top.
Okay, sir.
Sir, one thing I would like to ask: if we are choosing a scale of our choice, then is there any thumb rule for choosing? Like if we choose with an inappropriate value, then the scale, the chart might go outside the sheet, or like.
That's right. That's right, beta. Now the values which I have given you, like 1:5 million, this will ensure that about 80 to 90% of the charts will be fitting in your answer sheet. If you remember this 1:5 million, that will 90% of the time it will fit the chart in your answer sheet. But let's say that the chart is not fitting in your answer sheet. You picked up a scale, the dimension is not fitting in your answer sheet. What you do is you make a rough diagram of the graticule and you mark the dimensions, label them. Like we saw in this particular diagram, the dimensions are labeled. Okay, so make a rough diagram, not to scale, but label these dimensions well and make a mark also there, make a remark also there in the answer that since the chart is not fitting, we are making a indicative diagram and all the dimensions are mentioned.
Okay, sir, understood.
Okay.
Sir, in the Mercator chart, we also always measure distance in nautical miles, sir, but here we are calculating in mm.
That's because, beta, we are making this on our answer sheet, and the only way to measure on our answer sheet is the scale, which gives us millimeters and centimeters. Right? So that is the reason we have to convert all the dimensions in millimeters. That's the only way to make it on our answer sheet.
Okay, sir. So we need to draw as per the scale only. We cannot roughly draw the diagram and just show the distance like that.
No, cannot do that, beta. You have to calculate all these dimensions and show them in the diagram.
Because on the scale we have in centimeters, now we have to show them in millimeters.
Millimeters are better because you see, if you were taking centimeters, right, then 36.7 and 37.1 will both be rounded off to 3.7. So you will not be able to show the difference between them, beta.
Okay, sir.
29 to 30 will be 3.7, 30 to 31, 3.7, 31 to 32 will also be 3.7. So you will not be able to appreciate what is the change coming in. That's why millimeters.
Okay, sir.
Okay.
So if the reference lat is not given in the question, we have to take the mean lat of given latitudes, right?
Yeah, you can take the mean latitude of the limits given. Okay, great. So shall we close this out?
Sir, what was the use of this mean latitude, sir, in this question, what we have done right now?
Beta, he was asking it out that in case the latitude is not given with the scale, like they had given us latitude 30 degrees north. So in that case, you can take the mean latitude as your reference latitude. Clear, beta?
And sir, this mean latitude 30 degrees, north. How we have used this one in the formula?
Beta, in the formula we had a cos latitude in the denominator, na? So which latitude we
Okay,
put there?
okay. Yes, sir. Yes, sir. Okay, okay. Yeah. Okay.
Okay, all right. Understand what is the true sun, the mean sun, what are the different times, and then what is equation of time. Let's go. In this presentation, we are going to learn some of the concepts related to time in navigation. We have seen time being referred to as mean time or apparent time or sidereal time. We will see in this presentation what do we mean by these three different types of times. Also, we have seen that the sun being referred to two different types, true sun or the apparent sun and the mean sun. So we are going to understand what are these two different types of suns. Now to start with, let's go a little bit back in history. When we started measuring the time, we measured the time with the help of the true sun, the actual sun, the apparent sun which we see in the sky. That time we used to have sundials. The shadow of the sundial used to indicate the time on a scale. Now when we started measuring time using the sundials, we came to know that the unit of time which we measured using the sundial is not of a uniform duration. So the time as indicated by the true sun, also known as apparent sun, which was through a sundial, is not of a uniform duration. To give you an example, 1 hour of time in the month of January may not be same as 1 hour of time in the month of June. So when we observed that it is not a uniform duration, we came to know that we cannot use this reference of time as a standard unit. A standard unit should not vary. It should be of a standard duration. Now, why does the time measured by the true sun is of a non-uniform duration? How does the time keeps on changing? The duration of time keeps on changing. This is because of the elliptical shape of the Earth's orbit. The orbit of the Earth around the sun is elliptical, and when the Earth is moving in its orbit, the motion of the Earth is a non-uniform motion. It does not move with a fixed speed. The speed keeps on changing. This is as stated in the Kepler's laws of planetary motion, that all the planets orbit around the Earth in elliptical orbits, and the speed of the planet when it is moving on that elliptical orbit keeps on changing. Whenever it is closer to the sun, the linear velocity of the planet increases, and whenever it goes far away from the sun, the linear velocity of the planet in its orbit goes down. So it is basically because of this reason that the time indicated by the true sun is of a non-uniform duration. Because as the speed of the Earth keeps on changing in its orbit, the relative speed of the sun moving in the sky also changes. The second reason why the time measured with true sun is of non-uniform duration is that our measurement of time is with respect to the longitudes, with respect to the poles, and the motion of the sun is along the ecliptic. Ecliptic is inclined at an angle of 23.5 degrees approximately to the equinoctial. So this also brings in some non-uniformity. When the sun is close to the equinoctial and when the sun is at maximum declination north or south, it leads to a slight change in the duration of time. Now, we cannot therefore use the time measured by the true sun as a standard unit of time. So what was done to take care of this problem? To have a standard unit of time, astronomers have invented a mean sun, which is a fictitious body, and it is imagined to move at a uniform rate or a uniform speed along the equinoctial. This uniform speed is equal to the average or the mean rate of motion of the true sun on the ecliptic. So what we did was we invented a fictitious body known as the mean sun, and we calculated the mean speed of the sun throughout the year. For one complete full orbit, we calculated the mean speed with which the sun moves, and the mean sun was assumed to move at that particular speed only. Second thing, mean sun was assumed to move along the equinoctial and not along the ecliptic. So using this body, mean sun, we took care of both the issues, both the problems which the true sun had. One, the motion was non-uniform, so mean sun is assumed to move at a average speed or the mean speed of the sun. And secondly, it was moving on the ecliptic, inclined at an angle of approximately 23.5 degrees to the equinoctial, whereas the mean sun which we assumed that it moved on the equinoctial. Now the time which we measured with reference to the mean sun is known as the mean time. Like say for example GMT, that is Greenwich Mean Time, and it tells us that it is based on the mean sun. The time which is referred to the true sun is known as the apparent time. Now with this basic understanding of the true sun and the mean sun clear in our mind, let's go into the definition of the mean time, the apparent time, and also the sidereal time. We will try to understand what do we mean by these times. So first we go into the definition of local mean time or LMT. Local mean time or LMT is the westerly hour angle of the mean sun measured from observer's inferior meridian. So what is this LMT? This LMT is the westerly hour angle. From where is this westerly hour angle measured? It is measured with reference to the observer's inferior meridian, and up to which point it is measured? It is measured up to the mean sun. Let's try to understand it using one diagram. Now let's assume we are looking at the earth from top of the North Pole. You can see the earth coming up on the screen. Exactly in the middle we have the North Pole here, and let's assume that this meridian which we see, the dotted line which we see in the diagram, is the Greenwich meridian. Exactly opposite to it, in the opposite direction, we will have the 180 degree meridian. So 180 degree meridian also comes up on the screen. Now let's assume that we have an observer located at this particular location. Let's mark off the observer's meridian also. Now you see this dotted line coming up marking the observer's meridian. Exactly in the opposite direction, reciprocal to it, will be the observer's inferior meridian. So in our diagram, looking from top of the North Pole, we have the Greenwich meridian, 180 meridian, observer's meridian, and the observer's inferior meridian. Now let's assume that at a particular instant, the mean sun is at this particular location. You can see the mean sun coming up on the screen. Let's draw the meridian of the mean sun also. This is the meridian of the mean sun. Now before we go into the definition, one important thing to understand here in this diagram, that when we are looking from top of the North Pole, the clockwise direction represents the westerly direction. This hemisphere which you see on the right side is the eastern hemisphere. The hemisphere which you see on the left side of the earth is the western hemisphere, and the clockwise direction represents the westerly direction. So now we can go into the definition of the LMT. This red color arc which you see, the red color angle which you see, is the local mean time for this particular observer. Let's
So why
try
it
to
is
match
from
it with the
inferior
definition.
meridian, sir?
LMT is the westerly R angle. So you see the direction of this red color arc and angle is the westerly direction as represented by this arrow. It is the R angle of the mean sun. You see we have measured the angle up to the mean sun, and it is measured from the observer's inferior meridian. So starting from the observer's inferior meridian, this is the observer's inferior meridian, going in the westerly direction and going up to the mean sun. This particular angle is what we call as the LMT, local mean time.
Sir, it should be from observer's meridian, right?
No, beta, it is measured from observer's inferior meridian. When the sun is on your meridian, it's 1200 hours, beta. It's not 00 hours.
Okay, sir.
Okay. Now you can ask a question that why it is measured from inferior meridian? Why not observer's meridian? Right? The answer to that is that if you take reference from the observer's meridian, then the date change would occur during noon time, exactly in the middle of the working day. So it will interfere with our day-to-day operation. Suddenly the date getting changed during noon time will interfere with day-to-day operations. So that's why they selected the reference as the inferior meridian. So sun will be crossing the inferior meridian close to midnight, and that is the time when the date change happens, and it does not interfere with our day-to-day life.
Okay, sir.
Okay. This can be denoted in a angular unit, that is degrees and minute, but the normal mode in which we denote the times are in hours, minute and seconds. How to convert the angular unit to hour unit? We know 15 degrees of angle is equal to 1 hour. How did we get this conversion figure? We know 360 degrees of meridian. When the sun moves around 360 degrees of meridian, it constitutes 1 day, which comprises of 24 hours. So 360 degrees refer to 24 hours, telling us that 15 degrees is equal to 1 hour. So using this conversion factor of 15, we can convert this angle into hour, minute and second, and vice versa. Let's now go into the definition of Greenwich Mean Time, or GMT. It is very similar to LMT. GMT, or Greenwich Mean Time, is the westerly R angle of the mean sun measured from inferior meridian of Greenwich. Let's have the same diagram coming up on the screen. Looking at the Earth from top of the North Pole, you can see the Earth, the North Pole. We have the observer also here in the same location, and we have the Greenwich meridian, 180 degree meridian. Let's assume the mean sun at this particular location. Let's draw the meridian of the mean sun. Now GMT is referred to by this red color arc and angle. So you see GMT is the westerly R angle. You can see this angle is measured in the westerly direction. It is the angle of measured up to the mean sun. So you can see it is measured up to mean sun, and it is measured from inferior meridian of Greenwich. You see the angle is measured with reference to inferior meridian of Greenwich. So starting from inferior meridian of Greenwich, going clockwise in the westerly direction up to the mean sun, this particular angle gives us the GMT. So very similar to LMT, only thing is the reference meridian for LMT was the observer's inferior meridian, and the reference meridian for GMT is the Greenwich inferior meridian. Let's now try to see the definition of local apparent time, or LAT. Looking at the word apparent, we know that it is referenced to the true sun. The GMT and LMT were referenced to the mean sun, but the LAT and after this the GAT, local apparent time, and Greenwich apparent time are referred to the true sun. So LAT is the westerly hour angle of the true sun measured from observer's inferior meridian. Let's have the same diagram which we referred to for GMT and LMT. You see the Greenwich meridian, inferior meridian, observer, and observer's inferior meridian all coming up. Now let's assume we have the true sun at this particular location. So we have the meridian of the true sun also. Now westerly direction is the clockwise direction. This red color angle which you see is the local apparent time. So LAT is the westerly hour angle. You see it is measured in the westerly direction of the true sun. You see it is measured up to the true sun, measured from observer's inferior meridian. The starting point or the reference is the observer's inferior meridian. So starting from the observer's inferior meridian, going in the westerly direction up to the true sun, this particular angle gives us the LAT at any particular instant for this particular observer. Let's now see the Greenwich apparent time, or the GAT. Greenwich apparent time is the westerly hour angle of the true sun measured from the inferior meridian of Greenwich. So we have the same diagram on the screen. We have the Greenwich meridian, its inferior meridian. We have the true sun and the true sun meridian also. We have the westerly direction shown in the diagram. Now this red color angle which you see is the GAT. It is the westerly hour angle. You see it is measured in the westerly direction of the true sun, measured up to the true sun, measured from inferior meridian of Greenwich. The reference point or the starting point is the inferior meridian of Greenwich. So starting from inferior meridian of Greenwich, going in the westerly direction up to the true sun, this particular angle is called as Greenwich apparent time, or GAT. Now let's move on to the sidereal times, local sidereal time LST and Greenwich sidereal time GST. Local sidereal time, or LST, is the westerly hour angle of the Aries measured from the observer's meridian. Now we are aware that the word sidereal means referenced to first point of Aries. In case of stars also, we get their hour angle from the almanac as SHA, sidereal hour angle, and this SHA is measured with reference to first point of Aries. So likewise, the sidereal time are also measured with reference to Aries. So LST is the westerly hour angle of the first point of Aries measured from the observer's meridian. Now an important difference which you will notice here in this sidereal time is that in this case it is measured from the observer's meridian. The mean time and apparent time were both measured with reference to the inferior meridians, but the sidereal times are measured with reference to the observer's meridian. So let us show it in a diagram. We use the same diagram looking at the Earth from the top of the North Pole. We have the Greenwich meridian, 180-degree meridian, observer meridian, and the observer's inferior meridian. Now let's assume we have first point of Aries represented by this symbol at this particular location. We have the meridian of the Aries also coming up. The westerly direction also comes up on the screen, which is the clockwise direction in this case. Now this red color angle which you see is the local sidereal time. So you see, starting from the observer's meridian, going in a westerly direction and going up to the first point of Aries. This angle gives you the local sidereal time. You can check it with the definition. LST is the westerly R angle. You see it is measured in the westerly direction, which is the clockwise direction in this diagram. Of the Aries, you see it is measured up to Aries, and it is measured from the observer's meridian. The starting point is the observer's meridian. This is local sidereal time. Now moving on to the Greenwich sidereal time, or GST. Greenwich sidereal time, or GST, is the westerly R angle of the first point of Aries measured from the Greenwich meridian. So very similar to LST, only difference is the starting point instead of the observer's meridian now is the Greenwich meridian. So we have the same diagram coming up. You have the westerly direction marked clockwise. Now this particular red color angle which you see is the Greenwich sidereal time. So GST is the westerly R angle. You can see it is measured in the westerly direction, clockwise direction. Of the first point of Aries, you see it is measured up to first point of Aries, and it's measured from the Greenwich meridian. This is the Greenwich meridian. Starting from the Greenwich meridian, going in the westerly direction or the clockwise direction up to the first point of Aries, this particular angle gives you the Greenwich sidereal time. Now whenever we make this diagram, as a reference, we always show the Greenwich meridian at the bottom. The Greenwich meridian is shown at the bottom, and all the other references can be drawn with respect to the Greenwich meridian. Now, all these 6 definitions which we have seen, that is the local mean time, Greenwich mean time, local apparent time, Greenwich apparent time, local sidereal time, and the Greenwich sidereal time. All these definitions, all these terms are used sometimes in the numerical based on time. So the questions which you will have coming in the paper will have these terms as reference. So till the time these definitions are not clear in your mind, you will not be able to attempt that question. So the first step to attempting the time numericals is having these definitions clear in your mind. Once you have understood these definitions, you should memorize them, and whenever one of these terms is used, say for example Greenwich sidereal time is used, this should come to your mind that this Greenwich sidereal time is giving me the westerly R angle of the first point of Aries from the Greenwich meridian. Once this concept is clear in your mind, you will be able to make this drawing, specify this angle in that drawing, and that will help you to solve the question. A understanding of all these 6 definitions, clarity of all these 6 definitions in your mind is a must before attempting the time numericals. Now, having understood the mean time, apparent time, sidereal time concept, we now move on to the concept of equation of time. What is this equation of time? At the first glance, it appears to be an equation, a mathematical equation, but it is not an equation. Equation of time is basically a duration of time. Equation of time is the difference between the mean time and the apparent time measured from the same meridian at any particular instant. Basically, the equation of times tells us that the mean sun and the true sun are how much far apart. What is the time difference between the mean sun and the apparent sun? Say for example, if the mean sun is on my meridian right now, even though it's an imaginary sun, let's assume the mean sun is on my meridian. After how much time the true sun is going to come on my meridian, This difference or this duration of time is called as the equation of time. So it is a duration of time and is expressed in minutes and seconds of time. We know that the mean sun moves with a uniform speed, uniform lateral speed on the equinoctial, but the true sun keeps on changing its speed because of Kepler's laws of planetary motion. The true sun's speed keeps on changing. So at a particular point of time, it is possible that the true sun is moving faster and the mean sun is left behind. And at another time, it is possible that the true sun is moving a little slower and the mean sun takes over and is running ahead. The difference between these two is given by the equation of time. Now, if the mean time is greater than the apparent time, that means the mean sun is ahead of the true sun, the equation of time is considered as positive, and if the apparent time is greater than the mean time, or in other words, you can say if the true sun is running ahead of the mean sun, the equation of time is considered negative. So the sign of the equation of time, whether it is positive or negative, tells us which of the two suns is ahead in the race. If the equation of time is positive, the mean sun is ahead, and if the equation of time is negative, the true sun is ahead. The maximum value of the equation of time throughout the year, year after year, the maximum possible value of the equation of time is 16 minutes and 22 seconds. That is the maximum difference which can happen between the two suns. The equation of time at the meridian passage time of the sun can be easily obtained as whatever is the meridian passage time minus 1200 hours gives you the equation of time correct to the nearest minute. So you can use this simple formula to get the value of equation of time from the almanac for any particular day at the time of Marpas. Now for any other time of the day other than the meridian passage time, it can be obtained from the almanac as it is given on the daily page for 0000 hours and 1200 GMT hours. Like if you see at the bottom of the right side page of the almanac, under the column of the sun, you will see the value of the equation of time given for 00 hours and 12 hours at Greenwich in GMT. So you can see on this particular day, 7th day, the equation of time value at 00 hours was 11 minutes and 01 seconds. At 1200 hours, the equation of time became 10 minutes and 54 seconds. Now for any intermediate time, if you want to find the value of equation of time for any time between 00 and 1200, you can interpolate and find out what is the value of the equation of time. Equation of time is considered positive if the mean sun is ahead and is considered negative if the true sun is ahead. Any doubts, beta? Okay, beta. Great. So that was about the time, equation of time. So I'm closing the presentation now.
Sir,
Go ahead.
Sir, I have a query about this equation of time one.
Go ahead.
Sir, in almanac page, if we are looking August 31st and 1st September.
Right.
So there are some different marking is there, sir. Can you explain this one, sir? Like
Beta,
if first 1200 hour and first September 00 hours, sir.
Okay, beta. What marking is there, beta?
Underline, sir, this one.
Okay, okay. Now, beta, if you see a line, equation of time, you see a line somewhere, it is basically telling you that at that time, one of the suns is crossing the other one. Either the true sun is going ahead or the mean sun is going ahead. So that is denoted by marking a line in the almanac.
Yes, sir. So if
Got
a
it?
time frame is coming between that, then there will be same way we can solve, or there should be something else.
Yeah, same way you can solve, beta. No issues.
Because we can see on 31st 1200 it is given 00 minute 12 second, and then it
Okay.
will become first 00 hour 0003, and then it start increasing, sir. Means first
Okay, beta.
decreasing and then increasing.
इससे पिछले वाले पेज पे मुझे बताओ कि मरपास टाइम सन का क्या है, पेज बिफोर दैट.
12 hours 02 minutes.
Very good. So 12 hours 02 minutes is the Marpa's time before this line. Okay. So what is the equation of time?
Sir, before this page means on 24th August, it was Marpa's time 12 hours 02 minutes.
Very good. So 1202 basically means equation of time क्या होगी? अभी मैंने formula आपको बताया 1200 minus 1202 minus 2 minutes.
Yes sir, minus 2 minutes.
इसका मतलब है मीन सन पीछे है. नेगेटिव मीन्स मीन सन पीछे है, ट्रू सन आगे है. ओके. अब आप 31 के बाद वाले पेज पे देखो, आपका जो हमारे पास टाइम है इट विल बी लेस देन 12. सी नेक्स्ट पेज आफ्टर 31.
Yes sir. So from 12 September it was 11 hour 56 minute.
Very good. 1156 tells you that the equation of time is 1200 minus 1156, which is plus 4 minutes. So the mean sun has gone ahead. And it is at that line that the mean sun has crossed the true sun and gone ahead.
Yes, sir.
Clear, beta?
This page, Marpa's time is given only 1200, all 3 days, 31st, 1st and 2nd.
Yeah, that's right. Because jo Marpa's time hai, its accuracy is only up to seconds. Sorry, only up to minutes. It is not given up to the accuracy of seconds.
The Marpa's time is given of true sun.
It will always be of the true sun, beta. All the data given in the almanac is for the true sun. No data for mean sun is available because mean sun is not visible. It is imaginary.
Yes, sir. Imaginary. Yes, sir.
Okay.
Okay, sir.
The declination, GHA, Marpas, everything is of the true sun.
Okay, sir.
Okay. Great, beta. Congratulations. With this, we complete our syllabus of navigation. And now you can go full ahead into the assignments. And after the assignments, you can go into past papers. Whatever doubts keep coming to you, you can keep on sending those doubts on the group and we will resolve those doubts. Raghav, you had some doubts, beta? Kitne doubt hai, beta? How many questions? Okay. Okay. Can you read that question, beta? Okay, got it, beta. Doubt क्या आ रहा है? Okay, here it is, beta. No, nowhere. No, you don't need to make this anywhere. Just make the true altitude, beta. Right? You see, this is the pole. This is the polar distance, beta. And this is the true altitude. So you can see latitude is elevation of the pole, which is SP or PS. It is equal to polar distance plus the true altitude. Oh, not required. Not required. If you want, you can just, you need not calculate it also. Not required.
Sir?
Go ahead, beta.
Sir, in question number 13, yesterday you explained, so finding out the this calculation of Aries, sir. This first we calculate the value of P, and then from P we will go reverse in the calculation for Aries. So this 80 degree whatever value we receive.
Right.
So as per diagram, it will become here, or sir, it will be comes on
नहीं
the
बेटा,
other side of the.
ये ना यहाँ पे गलत बना हुआ है, ये यहाँ पे आएगा.
Correct, sir. जी, yes, sir.
बिल्कुल सही है बेटा. सो मुझे पता चल गया तुमने ये सवाल किया है, ये यहाँ पे आएगा बेटा. You are right.
Because LHA का आपने measuring बताया था from pole to western direction, then it
That's
will
right.
become 65 degree. So
That's
this
right,
angle will
beta.
be 65 plus addition with the 15 degree.
Yes, that's right.
And in question number 24, sir.
Go ahead.
Sir, can you explain the diagram, sir? Because this one added 100 degree, then this one another. So we calculate the P1 and P2, but sir, if you explain the diagram, so it will be good, sir. Question number 24.
Okay, beta. Basically, the doubt is coming कि ये 96 कैसे आया?
नहीं, 96 that is coming from twilight, no sir, 6 degree
Okay.
added and then plus additional 6 degree added.
ठीक है. तो डाउट किस में है बेटा? 100 में?
Yes, sir.
Okay. देखो बेटा, सन की डेक्लिनेशन है नॉर्थ.
Okay.
करेक्ट. सन
Yes,
की
sir.
डेक्लिनेशन नॉर्थ है, इसीलिए हमने जो डेक्लिनेशन सर्कल है, वी हैव मेड इट नॉर्थ ऑफ द इक्विनॉक्शियल. नाउ फ्रॉम द पोल, if you go up to the equinoctial, up to here, it is 90 degrees.
Okay.
And from the equinoctial up to the declination circle, this is equal to the declination.
Yes, sir.
Okay. So this side px will be 90 plus declination.
Okay, okay, sir.
Okay. Declination was 10. So it becomes total 100.
100. Yes, sir. This is 10 degree north and this was 90 from pole. Yes, sir.
Okay, beta.
Yes, sir.
Okay. Great. Very good. Okay. All right. Great, beta. Very good. So do the remaining questions also. अब ऐसा करते हैं बेटा, बाकी के. हाँ, go ahead.
Sir, I had a doubt regarding this ये LMT GMT का जो direction है, because we were in North Pole, the direction was clockwise. अगर South Pole होता तो anti-clockwise होता.
We generally do not show this basis the South Pole. ये हमारी मर्जी है हम कौन से पोल से इसको explain करते हैं. So it is not that you will need to do it for a specific observer. Okay, not required.
Question में ऐसा कुछ आ जाए कि observer position is in south.
ये जो टाइम की डायग्राम्स हैं, irrespective of wherever the observer is, north hemisphere or south hemisphere, it has got nothing to do with latitude. You can make it looking from the North Pole in all the conditions.
So direction will be the same, clockwise.
It will be the same.
Oh, okay, sir. Thank you.
Okay.
Sir, I have one doubt. Sir, in assignment number 3, question number 3 and 5. In question number 3, they have given a horizon during PM nautical twilight. So PM nautical twilight means we are taking SHA from sunset to nautical twilight. Why is it, sir, we are taking from sunset?
Okay, beta. Listen carefully. Nautical twilight definition says from sunset to 12 degrees below the horizon.
Yes, correct, sir.
So that's why we are taking from sunset to 12 degrees below the horizon. Okay. Now the doubt arises, why in question number 5 we are taking from end of civil to 12?
Correct. Yes, sir.
Now that is because in question number 5, along with nautical twilight, they have also mentioned suitable for sight. So we have to comply with both the conditions. Even though nautical twilight is from 0 to 12, 0 to 6 period, no stars will be visible. If they are not visible, they will not be suitable for sight. We cannot take any sight. That is the reason why we have started our observation from 6 degrees to 12 degrees. Because it is only that period which satisfies both the criteria. It falls within nautical twilight also, and it is suitable for sight also.
So basically, in civil twilight, the stars are not visible. In question number
That's
5.
right. That's right.
Sir, we have
In
also
question number 3, in question number 3, they have given that PM nautical twilight. So we are taking from sunset to the nautical twilight. That means civil twilight is also included in that. Why should we include civil twilight in that, sir?
No, beta. No. See, when you say nautical twilight, civil twilight is automatically included in that. It is not that civil is different and nautical is different. Nautical contains civil also. If somebody tells you astronomical twilight, it will consist of, it will contain the nautical as well as civil twilight in it. They are not three separate things. Okay. Did you understand?
Yes, sir.
Okay.
Sir, in this assignment, sir, question number 19, sir, for making the for summer solstices question, sir. Question number 19, sir.
Okay, let's go to 19. डाउट बताओ बेटा 19 में
सर इसका सर अप्रोच ही नहीं हो रहा था सर ये समर सोलेस्टियल्स वगैरह वर्ड्स यूज किया था
ओके बेटा समर सोल्स्टिस बड़ा सिंपल चीज है इसका मतलब है समर सोल्स्टिस का सिंपल एक मतलब है कि सन की जो डेक्लिनेशन है
यस सर
ये मैक्सिमम नॉर्थ है ये होगी 23 डिग्रीज 26.7 नॉर्थ बस इतना ही मतलब है ये आपको याद रखना पड़ेगा समर सॉल्स्टिस पे डेक्लिनेशन ये होती है अगर विंटर सॉल्स्टिस हो तो यही वैल्यू साउथ बन जाएगी
ओके सो डेक्लिनेशन इज गिवन दिस वन 23 डिग्री 26.7
दैट्स राइट
ओके sir here you calculate this two value p1 p2
yes
then minus and then plus sir additions so
okay हमने बेटा ये दो एंगल कैलकुलेट किए बिगर एंगल P एंड स्मॉलर एंगल P इन दोनों का हमने डिफरेंस निकाला वो डिफरेंस आया ये वाला एंगल
यस सर
ओके एंड बेसिकली जो ट्वाइलाइट पीरियड है वो इन्हीं दोनों के बीच में है
यस सर
तो हमें जब ये एंगल पता चल गया हमें पता है सन कितने रेट से ट्रेवल करता है हमने इस एंगल को सन के रेट से डिवाइड किया हमें ड्यूरेशन मिल गई
यस सर ओके
as simple as that right beta
yes sir thank you sir
so that's what is done great
sir
okay hold on ऐसा करते हैं एक लास्ट डाउट आज के लिए ले लेते हैं रेस्ट ऑफ द डाउट्स वी कैन कीप फॉर टुमारो
ओके सर वन डाउट इज देयर इट इज अबाउट एक प्रीवियस क्वेश्चन पेपर में से एक क्वेश्चन था सोलर इक्लिप्स का कंडीशन फॉर द सोलर इक्लिप्स अभी सर उसको एक्सप्लेन करेंगे 3-4 लाइन में खत्म हो जाएगा सर 12.5 नंबर के लिए क्या लिखेंगे उसमें हम
बेटा डायग्राम बनाओ
ओके सर डायग्राम बना के एलोंगेशन दिखा के सब कुछ एक्सप्लेन करें एक पेज
Uh,
2 पेज में क्या सर कितना लिखे हैं उसमें सर?
No. Question is for how many marks?
12
12 and a
12 and a
half.
half. 12 and a half. I
Very
think,
good. So basically the issue is कि how do we balance the text in the question. एक तो बेटा diagram बनाओ. Diagram will carry about 5-6 marks. 50% of the marks are for the diagram. Make a diagram for solar eclipse and then write down the condition. Simple paragraph 5 या 6 point जो हैं वो तुम वहाँ पे लिखो and that's it. You will get 12 marks.
Okay sir, thank you.
Remaining 3 sessions, what we will cover, sir?
Okay, beta. We will have only tomorrow's session, and whatever doubts you have, tomorrow's session, I'm not going to teach anything new. Only your doubts, we will be covering those doubts, and tomorrow we are going to finish off. After that, you will practice, and any doubts which come, you will share them on the group. Hopefully, I will be able to address them over the group itself.
Okay, sir.
So
As per
free.
the schedule, we have 3 more, but we have covered earlier.
Right, beta. Right. These are basically kept as spare classes, beta.
Okay, sir.
सर उसको वो जो एक क्लास रहेगा सर सबसे लास्ट वाला दिन में करते हैं सर, सो दैट वी कैन कवर अप एवरीथिंग एंड मतलब 3 दिन का टाइम मिल जाएगा. और
डोंट वरी बेटा, कल तक जो भी डाउट्स होंगे वो कल कवर कर लेंगे. उसके बाद जो डाउट्स आते जाएंगे, यू कीप ऑन शेयरिंग देम ओवर द व्हाट्सएप ग्रुप. इफ देयर इज अ नीड फॉर टेकिंग ए क्लास, देयर इज नो प्रॉब्लम. Okay, we can arrange that class later on, but I hope that I will be able to address your doubts over the group itself.
Okay, sir.
Okay, all right. So shall we close out for today?
Okay sir.
Okay, sir. Thank you,
Okay,
sir.
beta. See you.
Thank you,
So
sir.
from my side,
Thank you.
everything is covered up. Tomorrow we will be picking up your doubts, and tomorrow is only a doubt session. So I'll see you tomorrow. Bye bye.
Yes, sir.